Hello. Good morning, everyone.
Morning.
Morning, sir.
Morning, sir.
Morning, sir.
Morning, sir.
So just to double check, can you hear my voice clearly? Yeah.
Yes.
Yes, I can hear it.
Okay. Thanks. Right. Vasti, can we start now or we want to wait for a few minutes?
Maybe it's up to you, sir.
Yeah.
Now or we can wait.
Yeah. How about the rest? Now 113. Last time 140 something, right?
Yeah.
Last time, yeah. Maybe we need to wait for a few minutes to make sure everyone can join our class today. So how about last week lecture? Everything okay? Especially for the PCA? Do you have any question to ask?
No, sir.
No, so that's good because for today lecture, we are still needs to apply all the knowledge that we learn in PCA. Okay, because PCA and LDA is not too much different, but this is a good point for today lecture because you already learned PCA, then the basic knowledge of PCA will help you to understand well in this topic. Vasti, this is a third week lecture.
Yeah, Pak.
Yeah, okay. So the rest of the lecture, Vasti will cover, or other lecturer will cover. How about another week? Do you will cover what, Vasti?
Yes, sir. After
Oh,
me and Mr. Mujono will cover the rest.
okay. Yeah. Okay, so I think we can start our lecture. Okay.
Recording in progress.
As you can see, the title, Linear Discriminant Analysis, or the short form is LDA. Okay, LDA. So LDA is the very similar concept to PCA. The main idea is we want to project. Okay, we want to project a high dimensional data or high dimensional feature to a lower dimensional space. For example, I already give the example related to biometrics. Okay, let's say you have a face image, facial image. Facial image is 100 by 100, for example. Then if you convert to single vector, it will be 10,000. 10,000 vector is very big. And then in this 10,000, we have noise, we have redundant features, we have higher frequency information, which is not so good for recognition purpose. Then we can use LDA to reduce it, to reduce to a lower dimensional space. Maybe from 10,000, we can reduce to 100 or maybe 50 or maybe less than that. And during our during the reduction process, we try to preserve, we try to, you know, to maintain rich information exists in the feature vector. This is the idea of PCA and LDA. Okay. Okay, now let's talk about classification process. What is the main issue of classification? Okay, LDA and also PCA, the purpose is to, you know, to support the classification process, to help, okay, classification process to produce a better performance. Okay, for example, let's say you have two class like this. Class number 1 is red, dotted red color, and class number 2 is dotted blue color. So if you see clearly, the boundary between two of this class is not linear. The boundary is not linear, and some of them, I hope you can see my cursor. Can you see my cursor?
Yes.
Okay.
Yes, sir.
Okay, that's good. So you can see some of them are overlapped to each other, which is not so good for separation process. So after applying LDA, we hope we can have one group of red here, one group of blue here, which is well separated. If we have well separated like this, then the classification process will produce a perfect result. Perfect mean is 100% recognition rate, because this is what we want. Okay, when we do the system, when we design the system to recognize something or to classify something, so our target is to produce the highest recognition rate. If we manage to get a perfect, which is 100%, so this is considered very good. But the problem is, some of the data point here, they are overlapped to each other, then the performance will drop. We will not get 100%. So now we try to apply LDA, okay? Apply LDA to make sure that this data point is well separated. Now, this is the idea that we want to cover in today's lecture. Okay, unfortunately, LDA have several limitation or drawback, which is we can see after this at the end of our lecture. And one of the problem is, let's say we have the data like this. Okay, this one LDA will perform in a good way, but if we have the dotted line here, if moved to this area, then LDA will have a problem. Then the solution of this is we need to use GMM, Gaussian Mixture Model. Gaussian Mixture Model is another data modeling technique, which is very powerful and widely used in speaker recognition, in speech recognitions, and it can overcome the limitation of PCA and also LDA. Okay, okay, but at this moment, let's focus on LDA first. Okay, okay, so we have an input vector. Input vector, this one, X, real number, D is dimension, okay, assigned to 1K discrete classes. So if we have an input vector, we want to assign whether to this class or to this class, red class or blue class. So it depends on the which data point our input vector fall in. If they fall in this region, then this input vector belongs to red class. If it fall under very close to this region, then our input vector belongs to the blue class. So it is very straightforward classification techniques. Okay, so assumption is classes are disjoint. Okay, classes are disjoint, which is the input vector are assigned to exactly one class because we have a separate line here. Okay, so divide input space into decision regions, which boundaries are called decision boundaries. This one just to explain what is a classification techniques. Okay. So just now we have like this, and now we want to have the well-separated class like this, which is linear classification. So we have a straight line here. Straight line here represent linear classification. Okay, linear classification. And for the linear classifications, the performance or the way how we classify is easier. Okay, easier because we have a straight line, then we just compare whatever fall above this line is belong to A, whatever data fall below than this line belongs to blue. So that's mean we have the classification process perform better. So this is the role of LDA. Okay, the role of LDA to make sure if we have two groups like this, they are very close, then after apply PCA, they are far away from each other. So when they're far away from each other, we can create a boundary line like this, a straight linear boundary line. So this is what we want. So if the data can be separated exactly by linear decision surface, they are called linearly separable. Okay. Okay, now try to have a look another example. We want to study iris flower. Okay, iris flower. So this is the iris flower that we try to measure from 3 different species. Okay, let's assume we have the iris flower, but for this kind of flower, it has different species. For example, we talk about durian. You know, we have 3 types of durian. So the same thing goes to iris flower. Okay, so for example, we have species number 1. Okay, represented by red color. The name is Setosa. And then species number 2, green color. And species number 3 is purple color. So these 3 species we represent, okay, in a feature space like this. Okay, after we apply the PCA, so we can see that they are not well separated. This is after we project using PCA. Okay, the features that we put it here is something like this. The samples in our study is 150 samples, and then 4 features that we have is this one: petal length, petal width, okay, sepal length, and sepal width. So this is 4 parameter. You just assume that 4 element in single vector. Single vector, you have 4 features. Feature number 1, feature number 2, feature number 3, feature number 4. And then from these 4 features, okay, these 4 features, you apply PCA that we studied last week. We apply PCA, then we limit the highest 2 eigenvector. That's why we have principal component 1 and principal component 2. From 4, we reduce to 2 vector. And then these 2 vector we plot in feature space like this. Okay, if you try to analyze in detail, all of them are overlap. For example, we have the red here, we have the blue, we have the purple here, and also we have the green here. So this one gives the problem during the classification process. That shows the PCA is still not so good for class separations. It is good for reducing the dimensions, but the class separation is not so good. So this is what we want to solve, okay, after we apply LDA. Okay, that's why I put it here. PCA may not be ideal for separate the classes well. The classes well. Okay, now let's have a look. What happen if we use LDA with the same features just now? Okay, for one vector, 4 elements or 4 value, we reduce to two value or 2 eigenvector. So we can plot again the tree of this species in feature space, low dimensional feature space. So we can have the red region here, green region, and purple region. So perhaps this is better. Okay, this is better compared to the PCA techniques. This is PCA, this is LDA. So after we reduce to low dimensional feature space, so we can see all 3 species are well separated, except very small region here. But the rest is good. It's well separated. That means if you apply the classification process, maybe the performance can reach up to 90% and above. Okay, 90% and above. So this is what we want to do with LDA. Okay. Okay, so now we want to see the idea of LDA. What is the idea of LDA? What is the process inside LDA? Okay, the basic idea is you need to use the basis vector or eigenvector W like this. It's very similar to what we do in PCA. We have the basis vector or we have the eigenvector that we compute. Okay, that we need to compute based on the eigenvalue and eigenvector. Then we select the highest eigenvector, and then we project our input X. We project our input X to the basis vector W. Then Y is your low dimensional feature space. Okay, Y is low dimensional feature space. So I repeat again, this is what you need to do in PCA, in LDA. Okay, you need to calculate the basis vector W, and then this is your original feature. Okay, if we have take a look on this, that means this X is 4 dimension of vector. We project to basis vector W or eigenvector W, and then Y is your low dimensional feature space. All right, low dimensional feature space. So this low dimensional feature space given by this. Okay, given by this. Okay, I'm sure this is not so difficult for you to digest because you already learned PCA last week. Okay, very similar to PCA. Now the problem is how to calculate W. How to calculate W. W for PCA and W for LDA is a different techniques to calculate. There are several procedures that you need to follow in order to get a proper value of W. It's not the same way as you do in PCA. All right. Okay. Do you have any question at this moment, at this stage? Maybe some of you now confused. What is PCA? What is LDA? Are you okay? Okay, if no question, then we can proceed. So if you have any question, just let me know, then we can discuss in our lecture. Okay, so I repeat again, PCA and LDA, the way that we reduce the dimension are same. We use the eigenvector. we project our original data X to the low dimensional vector or low dimensional eigenvector. And then we got a low dimensional feature space Y. This is the concept that we use for PHA and LDA. And then the only difference is how we calculate W. The only difference is what is the step by step to get eigenvector, which is W, right? Okay, so now let's have a look. What is the effect of W Okay. W that I mentioned here is the projection vector. Okay. Let's say this is your data point. We still deal with two class problem. Okay, red and also blue. Red and blue, two class problem. If your W, if your basis vector or eigenvector in this way, that means we project your original data X to this basis vector. So we project like this. That means this group will be blue, this group will be red. Okay. Assume we know the basis vector W, we can compute the projection of any point X, this is X, RD onto the one-dimensional subspace spanned by W. Okay. Threshold W naught, this threshold W naught, such that we decide on a C1 class 1 if Y higher than W naught. So when your data is plotted here, that we call it Y. Low dimensional feature space is Y. If data higher than Y, why not? That means if data higher than this, that means our class is C2. If your data less than W naught, which is in this region, then your class is C1. All right, so this is the way how you do the classification after projection process. Okay, after projection process. If the Y higher than W naught, we claim our input in C1 in class C2, sorry, C2. If your input less than this W naught, then our class is C1. It's very straightforward. Just compare two of these. The problem is how to get the best projection direction. How to get the best projection of W. Let's say if you project W like this, you will not get the best one, because if your W in this way, there will be the overlap in this region. I will show you here. Okay. Let's focus on the figure first, then we try to understand all the sentence here. Okay, let's say this is your data point, okay, blue and also red. So if your projection in this way, so you can see this region will be a big problem during the classification process. You know, this region will be a big problem during classification process. However, if we tune our directions to this way, we can minimize the overlap region. We can minimize the overlapping region. That means this basis vector is better compared to the previous one. Because we can try to minimize the overlapping region. Compared to this one, overlap region is quite high. You can see the blue class, you know, it fall until nearly to half of the red class, and same goes to class red. It fall 1/3 of blue class. So this is not so good for recognition purpose. All right, so just to mention again, even if data was linearly separable in RD, we may lose this separability. Okay, even if you see clearly in two feature space here, 2D, two feature space, 2D feature space. So this data is clearly well separated, right? So you can see the blue in this area, the red in this area is, we can create a boundary line here. That means it is good. The data is already good, well separated. But when we do the projection, okay, if we choose the wrong projection, then we will get the bad result here. Okay, we will get a bad result. In the original feature space, so it is clearly well separate, two of these. And after we apply LDA, okay, if you do not choose the best basis vector, then the projection will create the bad results. Okay, so that's why you need to find good basis vector W that span the subspace we project onto. Okay. So now approach. What is the approach that we need to use? What is the strategy that we need to use to maximize class separations? When we thought about maximize class separations, means that we want to maximize this. Blue, we try to push in here, and red, we try to push down here, below here. So they are far away from each other. So this is the concept refer to maximize class separation. Okay, the blue one we push to upper here, and the red one we push to the down here. So in between two of them, there are no overlapping region. Okay, there are no overlapping region. This is the concept refer to maximize class separation. So what we need to do is adjust component of basis vector. So we just need to control or adjust the basis vector. But there is a way, methods that we can use to get the best basis vector. Okay, then select a projection that maximize the class separation. So consider we have a two class problem. Okay, two class problem, C1 and C2. C1 and C2. This is C1, this is C2. And for each of C1 and C2, they have N1 point and also N2 point. N1 point is number of data point here. Number of data point for C2. And now we need to calculate mean. Okay, mean for class number 1 is 1 over N1 summations of Xn. And Xn come from class C1. Okay, and is subset of C1. And also we need to calculate mean class number 2, which is M2 equal to 1 divided by number of data point in class M2. Then here we write as N2 as given here. And also summations of data point exist in class class C2. Okay, now you have mean for class 1, mean for class 2. And then measure class separation as a distance of projected class. So we need to calculate distance between M1 and also M2. We want to get a distance between M1 and M2. And then we put here M2 minus M1. M2 minus M1, we get the distance. So for the M2 equal to projection basis vector M2 minus its projection basis vector M1. So because our target, we want to project, and also we want to measure the maximum distance between two of mean in class 1 and also class 2. Then we have here WT transpose M2 minus M1. Okay, and the magnitude of the W should be 1. You know how to calculate magnitude, right? In our last week lecture, I show you how to calculate this magnitude. So the magnitude must be 1. Okay, this is what we want to, this step by step how to calculate W. Okay, so find W. Okay, find W that can maximize this. Okay, and okay, projected classes may still have still small overlap. Okay, small overlap. And for the LDA is large separations of projected class mean and small within class variation, small overlap of classes. So for PCA, our vector, our basis vector that we want to calculate must be pushed mean between class 1 and class 2 as far as possible, but within class separation is small. But you try to group them as small as possible. Yeah, as small as possible. Group, I mean the distribution in each of this class, we try to make it as small, as compact as possible, or as small as possible. But the mean from different class as far as possible. Okay. So that's why, okay, if we have a look here, based on the basis vector that we managed to get it here, so we managed to maximize the between class separability. Okay, maximize between class. This is between class. We try to maximize between class, and we try to minimize within class. So within class here, we try to make it small. You know, the distribution of red, we make it small compared to this one. You know, this one is wider. You can imagine, this one wider. After we minimizing within class, then it's become slim or it become smaller. So this is what we want to do with the basis vector after we apply the projection technique. And then this one also, same to blue. It's become smaller, okay? But point between two of these is larger. It's larger, it's far away. So separate sample of distinct group by projection them onto a space that can meet two of these criteria. Two of these criteria. Okay. Another example that try to demonstrate what I explained just now. Okay. Well, we have two classes like this, blue and also red. If your basis vector in this way, so we project to this vector, so you can see clearly there is the overlap region here. Overlap region. That shows that this is not the good directions for us to use for projection. Okay, another way is with the same distribution of original data space, our projection is in this way. So our projection in this way, so we can see that our data is well separated for class red and also class blue. Okay, for the class red and also class blue. So this is the idea that we want to calculate with PCA, LDA. Any question from you guys? Any question from you? Everything okay? Yeah?
Okay, sir.
Okay, that's good. Okay. So now this is step by step how we need to, how we need to do in order to calculate a vector W. So in order to calculate vector W, this is step by step that you need to follow. Same to the PCA. We have PCA. It has its own way to get a vector W. Okay. So now let's say we have class CK. Okay. We have class CK. CK means our class can be 2, can be 3, 4, 5, 100, 1,000, 10,000. It doesn't matter. So we write our class label as CK, and we need to calculate within class scatter. Okay, within class scatter. So within class scatter means that you calculate the distribution in each of class. For example, we have class C1. So you just calculate the scatter in class C1. If you have class 100, then you calculate within class scatter in class 100, and the formula is this. So scatter K equal to summations, okay, of your original data. Okay, the projected data, okay, and then minus with mean in class K. M is mean in class K, and power of 2. This one is, we call it SK, scatter class. Okay, scatter class. And YN is the projected. YN is the projected data. This is your original data, okay, in class N. Okay, N refer to CK class N, and then this is projected data of class N, and this is mean. Mean K, projected mean. Mean K is a projected mean equal to W transpose MK. Okay, so for each of our class, we have this. Okay, we have this scatter, project output, low dimensional data, and also mean for the projected data. So our target is to maximize, okay, maximize Fisher criterion. So we want to maximize between class scatter divide by within class scatter. We want to maximize this. Between class mean, okay, between class mean scatter between two different class. This class and this class, we call it between class scatter. We want to maximize this, okay, maximize this, and at the same time, within class scatter must be very small. Within class scatter is this. Within class scatter refer to this, within class. Distribution within class must be very small, okay, very small. But between class scatter must be very big, must be very far away. So this is the criteria. We call it Fisher criterion. Okay, Fisher criterion. Fisher, I think this is the guy who found LDA, the the first person that found LDA. Okay. So between class scatter over within class scatter. So between class scatter is this lah that we calculate just now. This one between class scatter. Between class scatter, and then within class scatter is this one within class. So M2 minus M1 power of 2 over scatter 1 scatter 2 like this. So this one we substitute here. So we have W SB W transpose. This one scatter within scatter between class scatter within class scatter matrix, and this is our projection basis. So SB and SW given by this formula. Okay, SW given by this. This is our original X, data X minus with your mean. This one is original X minus mean transpose. Okay. And between class scatter is this, okay, this mean class number 2 minus mean class number 1 multiply with a transpose of this, okay. All right. So for K classes, okay, for K classes, we define the between class scatter, okay, for K classes. Just now we have class 1 and class 2. Class 1 and class 2. How about if we have multiple classes? We have 10, 15, 20, 100 classes. We define the between class scatter matrix as SB equal to NK MK minus mu. Mu is the average of the whole class. You can see here mu is 1 over n, summation of xi, I from 1 to n. Mu mean or average of the whole class, data point of the whole class. So I put here where mu is the global mean of data set. Okay, it doesn't matter your data set is class, how many class you have in your data set. So you need to calculate mean for the whole data set, okay, whole data set, and use this value to calculate between class scatter matrix. Okay, use this to calculate between class scatter matrix SB. Okay, SB. Okay, so now how to calculate the best value of W? How to calculate the best basis vector of W? Just now we understand that. So we want to maximize this. So the problem now, we know value of SB, we know value of SW, but we need to calculate value of basis vector W. Okay, the way to calculate a basis vector W is like this. We need to find W by setting dj over dw equal to 0. We need to integrate this. Okay, we need to integrate this dj over dw. Sorry, differentiate this dj over dw, and then the answer equal to 0. Okay, for this one, you will get SBW, W transpose S WW SBW after we apply this, based on this, minus W transpose SBW SWW equal to 0. WW equal to 0. And then SBW, you just rearrange this, SBW minus JSWW equal to 0. And then you divide by SW, then we have here divided by SW as well. So S minus 1 W SB W minus JW equal to 0. And then this one equal to S minus 1 W SB W equal to JW. So this one give you the eigenvalue problem. Okay, eigenvalue problem. So this one will give you eigenvalue problem. Okay, and then you need to use the computer software, okay, MATLAB or Scilab or Python, in order to calculate what is the eigenvalue and eigenvector of this. Okay, and then from the eigenvector that you calculate, maybe you will get a set of very big size of eigenvector. Then you need to sort. Okay, you need to sort based on the highest eigenvalue. The same process that you apply in PCA. Okay, the same process that you apply in PCA. Okay, you need to sort it. Then you get the W that you want to use for projection purpose. So that's why I put it here is similar to PCA. Okay, is similar to PCA. The rest of the process is similar to PCA. The only difference is the way how we get the a basis vector that we put it in this slide, in slide 15. So this is the process, and also this one also 3 of this slide shows the step by step how to calculate a basis vector W. Okay. Okay, at this point, any question from you guys?
Teman-teman boleh ya bertanya dengan bahasa.
Ya, boleh bertanya dalam bahasa Indonesia juga. Saya pun boleh paham lah bahasa Indonesia.
Silakan. Oke, kalau tidak ada saya saja.
Ya, boleh.
Professor Imran just want to make sure that LDA have the same basic idea as a cluster analysis, related within class and separated class. So we want to minimize within class, or we say a cohesion in cluster analysis and maximization the interclass cluster. Question, sir, what the difference between the calculating the distance between LDA and the partitioning clustering? The idea maybe.
Okay, what is different to calculate distance between LDA and partition clustering?
Yeah, they have a same basic idea. Yeah, they have a within class and separated class.
Okay. Okay, the idea is from based on my understanding, LDA we use when we need to deal with very huge data point. So your data point is very huge, then you want to project to the lower dimensional space. So when you do the projection, okay, we try to preserve the information between the SW within class and also between class. We try to maximize this. So in another word, I can say that we will have the optimum basis vector that we can project. And then after we do projection, we can calculate the distance. I think this is the similar concept to clustering techniques, except the clustering technique, maybe during the projection, okay, during the projection process, maybe you will not get the optimum, optimum low dimensional feature space. Maybe not low dimensional feature space. That's the only difference.
Oh, okay. Oh yes. It's same, almost same with a super vector machine, maybe, sir.
Yeah, support vector machine also same, because we want to see we have a boundary line here. Whatever upper than boundary belong to class 1, whatever belong to below boundary belong to class 2, right? But the problem is, in certain problem, the boundary is not easy to create. Maybe the boundary will overlap, maybe the boundary will be non-linear. That's the issue. That's the issue if we straight away use the SVM, support vector machine. So in classification process, we need to clear first our data distribution in low dimensional feature space. If our low dimensional feature space has a very nice data separation, then it is a guarantee to us our performance, recognition performance will be high. If our low dimensional feature space still has a overlapping region between class, then our performance for sure will not give the best performance.
Yeah.
Okay, yeah.
Oh, okay.
Mm.
For the LDA work on multiple class, it may be same with SVM. So it is use kernel data too, sir?
Yeah. LDA also we have the kernel techniques. We can introduce the kernel method in order to get a better separations in feature space. For example, in original feature space, our data is very to separate linearly. Then we need to use the kernel technique. They call kernel trick. So in the kernel trick or kernel method, we try to increase dimension of data. Instead of a 2D data, we push to 3D data. Is it right? Yeah. Okay. However, we still got a very several limitations on LDA and PCA. I will share with you after this. And that's why I try to introduce here GMM, Gaussian Mixture Model, which is more powerful method to do the data classification in a very extreme feature space. Okay, Basti?
Okay, sir.
Okay, maybe student lain mau bertanya pun boleh?
Oke, silakan para mahasiswa yang lain, teman-teman. Kelas Jason, Caroline, Hadi, dan Audrey, boleh silakan. Siapa yang bertanya? Atau kami kurang paham?
Ya, mungkin mungkin juga.
Formula, maybe. Ada?
Tapi tidak mengapa. After class, if you have any problem, you can email me. Okay, you can take my email, then you can email me if you have any anything you want to ask about PCA, LDA, and so on. I'm sure all of you now in year 3 or year 4, Basti?
In year almost 3.
Year 3. Okay, that means the whole course is year 4, right?
Yes, sir.
Yeah. Okay. All right. So if you do not have any question, then we can continue we can continue to have a look comparison between PCA and LDA in the actual problem of signal processing. Okay. So this is the this is the comparison between LDA and PCA. Okay. Okay. LDA and PCA. We want to classify a gas sensor array. Okay, gas sensor array. So we have the sensor response here. Okay, we have a sensor response here. Okay, so after we apply a PCA, we can have a look the low dimensional feature space 3D. In 3D, low dimensional feature space is like this. The classes, okay, the classes overlap to each other. Okay, so 5 types of coffee bean were presented to an array of chemical gas sensor. We want to check the coffee bean. Yeah, here one of the popular coffee bean, Sumatra and also Sulawesi, come from Indonesia. Yeah, so these two type of coffee bean compare with coffee bean from Kenya, from Arabian, and also from Colombia. So we want to check the, you know, maybe the gas produced by this coffee bean using gas sensor array. 5 type of coffee bean were presented to an array of chemical gas sensor. Okay, for each coffee type, 45 sniff were performed, and the response of the gas sensor array was processed in order to obtain a 60-dimensional feature vector. Okay, 60-dimensional feature vector. That's mean the original data produced by sensor is 60-dimensional. Okay, 60-dimensional. Each sensor produce 60-dimensional. Then we use PCA and also LDA. We project to 3-dimensional. That's mean we reduce for 57 feature vector, 57 features in our long vector. Okay. Okay, so the result from 3D scatter plot, it is clear that LDA outperformed PCA in terms of class discrimination. So here, class discrimination of a coffee is well separated in LDA space. Okay, compared to the PCA space, we managed to project to lower dimensional space, but you see the classes, okay, the classes are overlap to each other. Okay, the classes are overlap to each other. So you can imagine if you want to use SVM to perform classification, or if you want to use nearest neighbor, K nearest neighbor to perform recognitions, what do you think about two of these techniques? I'm sure LDA will perform better compared to PCA, right? Because as you can see here, the classes are well separated. So if you have any simple classifier, I'm sure it will perform better. It will perform better because we already manage our data at the early stage. Okay, we try to produce a very rich information or very good features that we can pass to classifier. Then finally, the classifier just do the matching task, which is very straightforward, right? So this is the idea of PCA and LDA. Okay. Okay. And again, we come back to our example on iris flower. Okay, on iris flower that we have a look in the beginning of our lecture. Okay, similar to PCA, we can use LDA for dimensionality reductions by looking at the eigenvalue problem. So it's very similar to the PCA that we do last week. Once we do the calculation of eigenvector and eigenvalue, what you need to do is you need to do the sorting of eigenvector based on the highest value of eigenvalue. If the highest value of eigenvalue demonstrate the very dominant basis vector, okay, that represent your data. So in LDA, magnitude of eigenvalue in LDA describe importance of corresponding eigenspace with respect to classification performance. So the magnitude, the value in eigenvalue, okay, shows a very important corresponding eigenspace with respect to classification performance. However, magnitude of eigenvalue in PCA, okay, this should be a PCA. Describe importance of corresponding eigenspace with respect to minimizing reconstruction error. So this is two projection. For PCA, we assume that our eigenvector will produce very minimum reconstruction error. But in LDA, our eigenvector, okay, will produce the better separations, okay, which at the end will contribute to the highest classification performance. Okay, so this is a difference between PCA and LDA. Okay. This is a step-by-step, the algorithm that you need to apply when you want to use LDA. Okay, so in our practical class, we do all of these things. First, you need to mean normalization. So we need to normalize mean value. Okay, normalize mean value and then compute mean vector. Compute mean vector. And then compute scatter matrix S omega SB. Okay, S omega and SB. And then compute eigenvectors and eigenvalue of S omega 1, SW and SB. You need to, first you need to manually compute S within class scatter matrix, between class scatter matrix, based on the formula that I shared just now. And when you know two of this value, okay, you can calculate eigenvector and eigenvalue. And then after you know the eigenvalue and also eigenvector, then you can put them in the array like this. Then you can sort them. You can sort based on the the largest eigenvalue. Then you can do a projection. When you know what size that you want to have in the low dimensional feature space, then you can take this W and perform the projection based on the basis vector that you decide just now. So I want to remind again, X is your original data, okay, original data, and Y is your low dimensional space. I put it here. X is your samples data and Y is the coordinate metric of the n data point that represent with respect to the eigenbasis. Okay, Vasti, everything okay? So this is step by step how to calculate PCA, how to calculate LDA. Okay, so now we want to have a look. Even we can see just now, LDA is very good for classification of our data in a feature space, but there is a limitation. There is still several limitations that LDA cannot solve. Okay, LDA cannot solve. Okay. LDA produce at most C-1 feature projection. Okay, LDA produce at most C-1 feature projections. If the classification error estimate establish that more features are needed, some other method must be employed to provide those additional features. Okay, that's mean when we do the classifications, we realize that the performance may be dropped. Then maybe you need more features. Okay, you need more features. You are required more features to put in the system. So that's why another method must be employed, must be used to provide additional features. Maybe you can have another stage of transformation. For example, we use Gabor features. We use wavelet features. Okay, you need additional pre-processing. Okay, additional pre-processing on your original data. before you can use LDA, because maybe the problem of data is not enough to do the estimation process. Okay, and also if you realize, if you want to do facial recognition, if you want to use PCA, if you want to use LDA, you need to have two image for training. Two image for training. If you have one image only for training, then you cannot use LDA. You only can use PCA. That's the limitations that we mentioned here. If you have single image for training, let's say you want to do facial recognitions, then you cannot use LDA. You only can use PCA. If you want to use LDA, you need to have more than one image for training, maybe 2, 3, 4, 5, 6, 7, it doesn't matter. That's the, because why we need this, because in our calculations, there is a parameter that we want to calculate, which is between class scatter matrix. Okay, we want to calculate between class scatter matrix. We have the parameter that we want to calculate here that required more than two classes. That required more than one training images. Okay. Okay, LDA is a parametric method since it assumes a unimodal Gaussian likelihood. In the PCA that we used just now, okay, we assume that our data is, our original data distribution is a unimodal Gaussian. It's a Gaussian distribution in a PCA that we, okay, let's have a look here. Okay, in the LDA that we use here, we assume that our data is fall under Gaussian distribution. Okay, like this, very nice Gaussian. One ellipse here, one ellipse here, very nice Gaussian. However, in certain case, we may have this situation where our data is not Gaussian. For example, like this. Class number 1 shape like this, class number 2 shape like this. This is not the Gaussian shape. Then we got a problem with LDA. LDA will not perform very well to find the basis vector if we have the distribution like this. Similar to this one, we have class 1 in this region, class 1 in this region, and then class 2, class 2. This is not in the single Gaussian distribution. Okay, it is not in the single Gaussian distribution. Then LDA will not perform very well for this kind of data. And same with this, we have a Gaussian shape of class 1 like this, and then overlap with Gaussian class number 2 like this. Then still we got a problem. Okay. Okay, and number 3, LDA will fail when discriminatory information is not in the mean, but rather in the variance of data. Okay, let's have a look at 2 of this class. So LDA will fail for this situation. Okay, because LDA will fail when this discriminatory information is not in the mean, because mean for class 1, mean for class 2, they are same. They have the same value of mean. The only difference between class 1 and class 2 are variance. So if you have this situation, then LDA will fail. LDA will fail to project our data to a better separation space. Okay. Okay, so any question about LDA? After this week, we will move to GMM, Gaussian Mixture Model. Okay, so if no question, Vasti, can we break for 5 minutes?
Sure, sir.
Yeah. All right.
I-
So then you can have a look your lecture notes to make sure that you manage to understand all the content for today's lecture. Okay, we break for 5 minutes.
Yes,
So
sir.
we come back at what time in Indonesia now? 9:13, right?
9:13.
9:13. So 9:20.
Yeah.
Yeah, 9:20. Yeah, we come back at 9:20.
Sembari nunggu, saya absensi kelas A dan B ya. Nanti kelas C dan D akan diabsensi oleh Pak Mul. Oke?
Oke, siap, Bu.
Oh ya, Pak. Jason, di kelas kamu ada yang tidak datang? Jason. Caroline, kelas kamu ada yang tidak datang?
Nggak ada yang izin ke saya sih, Bu.
Oke. Sebentar. Saya langsung absensi ya. Password kamu nggak berubah kan ya, Caroline?
Iya, Bu, sama.
Wah, Caroline ntar lagi ulang tahun ya, Caroline.
Iya, Bu.
Kelas Jason, ada yang izin ke kamu, Son?
Enggak ada, Bu.
Nggak ada. Password kamu masih sama, password?
Masih sama, Bu.
Oke. Saya sudah Pak Mul, mungkin dari kelas Bapak.
Baik, Bu. Bentar ya. Saya share screen aja ya. Minta bantuannya. Itu kelas C. Objeknya. Terima kasih, Audrey.
Sama-sama, Pak.
Tadi ada Hadi.
Ada, Pak.
Bentar, ya. Silakan.
Sudah, Pak.
Ya, terima kasih.
Recording stopped.
Okay, Wasti, can we continue?
Silakan, Profesor Imran.
Alright, terima kasih.
Recording in progress.
Okay, so now I share my notes on GMM. Okay, so just now we can see the problem of LDA. Okay, LDA that which is very difficult to perform for this kind of data distribution. And the solution of this is by using GMM, Gaussian Mixture Model. Okay, Gaussian Mixture Model is one of the techniques that is very popular in speech recognition, in speaker recognitions, because this concept, the framework is based on the statistical techniques, where the distribution of data is modeled using probability density function. So that original data point in the feature space, okay, original data point in the feature space is used, okay, to calculate a probability density function, PDF, probability density functions, and whatever data distribution, okay, whatever data distribution normally can be modeled accurately when we use enough components to represent GMM. Okay. Gaussian mixture models come from its name, Gaussian mixture. Okay, Gaussian mixture, several of Gaussian mixture. Okay, let's say this is our original data space, original data point in the feature space. So you can see it is not a simple Gaussian distribution that we see before this. So we have this shape and it's very high density here. And then there is some scatter here. Okay. Often we are given a set of points whose density we wish to model. So this is the point that we want to model. So we need to use the mixture model, which is more flexible. Okay, more flexible. We can create a Gaussian shape in this area, Gaussian shape in this area, Gaussian shape in this area. But this is 2D feature space. Let's have a look on the single 1D feature space. Maybe it is more clear to understand. So Gaussian mixture is a combination of several Gaussian here. So let's say our distributions is a combination of 3 Gaussian. Gaussian number 1, Gaussian number 2, Gaussian number 3. So we have 3 Gaussian in our system. Okay, that means our formula to represent this is Px equal to summation of Gaussian number 1. That's why we put a k equal to 1 to k. Component number 1, then component number 2, component number 3, which is k equal to 1 to 3. Component number 1, component into 2, component number 3. Okay, equal to Gaussian number 1 add with Gaussian number 2 add with Gaussian number 3. Okay, Gaussian number 3. And here is the magnitude that represent the weight of each of these Gaussian. For example, weight here is 0.7 maybe. Here is 0.1. This is 0.2 maybe the weight. So the summation of weight must be 1. Total number of weight must be 1. This is the idea of GMM. Okay, so we'll come back to this. Okay, maybe for this distribution, we can have also 3. Gaussian number 1 here, Gaussian number 2 here, Gaussian number 3 this way 3. That's why I mentioned just now, if we have like this, so Gaussian number 1 may be here, Gaussian number 2 may be here. So we have 2 Gaussian shape. And then for this class, Gaussian number 1, Gaussian number 2. So we only have 2 Gaussian is enough to solve this problem. This one also, Gaussian number 1, now Gaussian number 2. This one Gaussian, another Gaussian for class number 2. This one also same, Gaussian number 1 and Gaussian number 2. So that's why the Gaussian mixture model is very powerful and can be solved for the problem of data distribution where the LDA is not performed very well. Okay. So basically, when we want to use the Gaussian mixture model, we need to understand, we need to calculate all the parameters related to this model. The parameter that we want to calculate is number 1, weight. Pi k here is weight. And parameter number 2 is mu k. Mu k is mean for each of these Gaussian. This one, weight for each of these Gaussian. And and then we have average each of this Gaussian, average or mean, and then we have covariance, that represent the size of this Gaussian. So these three parameters we need to estimate or we need to calculate from our training data. So we have a training data, then training data for each class, then we need to calculate component for each class. Each class means, let's say, person number 1. Okay, person number 1. So you need to calculate all the parameter for person number 1. So if you have person number 2, then you need to calculate a Gaussian parameter for person number 2, and so on. So this is the idea of GMM. So the objective is maximum likelihood estimate of model parameter. We need to make sure that the model parameter that we want to calculate just now, okay, the model parameter that we want to calculate will produce the maximum likelihood estimate. Okay, will produce the very accurate coverage in feature space. So to make sure that this model is very close to the original data distribution, this is what's our aim to do the parameter estimation. Normally, the parameter in Gaussian machine model, if you have looked in any machine learning textbook, so they will use this symbol. Okay, theta symbol equal to pi k, mu k, and also covariance, and k equal to number of component. Number of component can be 1. If you use k equal to 1, that means you use only a single Gaussian. Okay, single Gaussian. If you use 2, that means you have two Gaussian shape. If you have 10, then we can use 10. For example, in speech recognition, maybe we can use up to 20 Gaussian shape in order to get accurate results. Using 1 or 2 is not enough for a very complex distribution. So that's why the number of components is very important. For a very complex distribution, number of components needs to be very high. But for the less complex distribution, number of components can be less. Maybe 1 Gaussian is enough to do the to create a probability density function that represent your data distribution in feature space. Okay, how to estimate? Okay, how to estimate the parameter? Okay, how to estimate the parameter? We will use the maximum likelihood estimate. Okay, maximum likelihood estimate. So when we estimate the parameter, we will calculate the log value. Okay, the log value by using this problem, by using this formula. Okay, log value. So basically, we will use the iterative. Okay, iterative means that we have multiple calculation process repeatedly until we get a maximum likelihood. So we start with the initial value, and then we calculate, and then we calculate the maximum likelihood, and then we run again. That's why we call it iterative scheme. Okay, for the parameter, for the learning parameter. This parameter we want to calculate because at the first stage we do not know what is the value of this parameter, but we know how many components. Let's say you set at the beginning, we want 10 components. Okay, 10 components, but we do not know the value each of this. So that's why you need to use iterative scheme EM algorithm for learning parameter. Okay, learning parameter. So GMM likelihood. Okay, so GMM likelihood is a process that we want to calculate the likelihood value. Okay, Likelihood value, we will use this formula. Okay. This one is multiplications. Okay. This one represent what? Represent GMM. This one, GMM. Likelihood. Why we put a slash sigma theta here? Because we refer to the specific class. Class number 1, class number 2, class number 3, class number 4. We refer to specific class. Okay. The process to calculate likelihood is become easier. Okay, it's become easier when we take log likelihood. Okay, we take a log function, because here when you can imagine this one multiply with another value here, multiply with another value. But if you put a log likelihood, okay, log likelihood, in log functions, the multiplications become summation. The multiplications become summation in log function, which is easier for you to calculate compared to this. Original likelihood, the original formula to calculate likelihood is like this, but another way which is more simple is like this. We use log likelihood. Okay, log likelihood. Okay, so now we want to find the parameter. Okay, we want to find the parameter that can maximize log likelihood, that will maximize our log likelihood in this formula. Okay, so in order to calculate the maximum parameter, okay, we need to differentiate like this. We need to differentiate log likelihood, because we have 3 parameters we want to observe. Number 1 is weight. Number 2 is mean. Number 3 is covariance. So we need to integrate. We need to differentiate to 3 of these parameters that we want to observe. DL over D mu K equal to 0, and this one equal to 0. We take this, we take this. And then DL over D covariance equal to 0. And so the last one, weight, equal to 0. This one equal to 0. Because we need to calculate 3 of these components. So iterative scheme for learning parameter in mixture models and latent variables model is the step-by-step like this. First, you need to choose the initial value. Okay, initial value. You need to choose mean, covariance, and weight. And then for each of these, you need to run iteratively. Okay, iteratively until converge. Okay, until converge, and you have 2 processes here. Number 1, E step. Okay, E step. Okay, so for the E step is evaluate the responsibilities. Okay, responsibility. Okay, which is a posterior probability of data point I belonging to mixture component K, and also we have M step. Okay, M step is use the updated responsibilities to re-estimate the parameter, 3 of this parameter. So every step in EM algorithm increase the likelihood function. So converge, check, log likelihood or parameters. So converge means when the value doesn't move, then you need to check the parameter and also check log likelihood. Then stop it and then take this value as the best component that represent your distribution. So basically, for the GMM like this, you need to calculate the parameter that best represent your distribution. The method that you use to calculate this parameter, we call it E step, EM. expectation step and also maximization step. So in E step and M step, it is just the iterations, a looping process until the value of log likelihood doesn't move, until you get the best value of log likelihood doesn't move, then it shows that this is the best, the best parameter that can represent, and copy this parameter, save in your database as the template, okay, as the template. Okay, so now I want to show in detail E step and also M step. So expectation step and also maximization step. Okay, first you need to initialize and then you need to calculate the E step, okay? The formula to calculate the E step is like this, okay? So you try to get the responsibilities RIK, responsibilities of this. And then you need to re-estimate the parameter, okay? We need to re-estimate the parameter of the weight, mean, and also variance, okay? Then the formula that you need to use is this, this mu k equal to 1 over nk summation RIK. You take out from here. You take out from here and put it here. Variance is 1 over nk summations RIK. RIK you take out from here and put it here. And then this one is weight k. So I think that's all for the GMM. So GMM is a little bit difficult compared to PCA and LDA because there are a lot of statistical techniques that you need to familiar for, especially when you are talking about probability density functions. So you need to be very you need to have a basic knowledge in statistics. But here I just want to introduce just to show that limitation of LDA that we found just now can be solved by using GMM. Okay, GMM. Maybe another method also can. For example, you can use the kernel techniques. We call it kernel tricks to to push your data from low dimensional feature space to higher dimensional feature space. But sometimes still in higher dimensional feature space, the distribution still got a problem where the LDA will not perform very well. So in that case, better for you to switch to the method related to statistical modeling, GMM, Gaussian Mixture Model. Just to share with you, my PhD work related to developing a GMM, Gaussian Mixture Model for biometric, facial and also palm print recognitions. So I realized that GM is very powerful methods to classify any distribution of signal. It doesn't matter whether the signal is vibrations, the signal is speech, or the signal is any real data from the sensor, from the environment sensor, or from the any data. Can be if you are in business, maybe you want to do forecasting, forecasting, stock analysis, and GMM will be very good for this kind of analysis. So it is not limit to the electric or electronic, but you can use to any data modeling, which is very good for for the complex data distribution. Yeah. Okay, Vasti, I think that's all for my lecture. So after this, we can have the practical class. Okay, I'm using MATLAB. Then I will share with you using Zoom. Maybe for practical class, maybe we can have a look last week a task. I will show again the PCA, and then we proceed with the LDA. Okay, LDA to just to make sure that you are familiar with this.
Okay.
So before I stop my lecture, maybe you have a question to ask.
Silahkan teman-teman kalau ada yang mau bertanya boleh pakai bahasa Indonesia yang baik ya, tapi
Ya.
atau boleh menggunakan bahasa Inggris. Silakan.
Pak Imran, saya mau bertanya.
Ya, ya.
Makanya kenapa harus dibuat distribusi Gaussian atau distribusi normal? Ada alasannya nggak, Pak? Karena kan distribusi itu ada banyak jenisnya.
Ya, ya. Saya ulang soalannya, kenapa perlu dibuat distribusi Gaussian ataupun distribusi normal?
Ya, betul, Pak.
Okay. Basically, when we deal with LDA, normally we assume that our data is normal distribution or Gaussian distribution. Even in actual data distribution, our data is not 100% normal or not 100% Gaussian. We just assume that our data is normal. Then we proceed with LDA step, which is not so accurate because our data is not Gaussian. But when we want to use LDA, we assume our data Gaussian. Then we use all the process in LDA and also PCA. However, in GMM, if you have very complex data like this, our data is not normal. It's not normal, but we want to use combination of several Gaussian function. We want to use a combination of several Gaussian Gaussian shape or normal shape to represent this. Because in statistics, we have Gaussian distribution, we have a binomial distribution, we have several distribution types. So the easiest way is a Gaussian distribution. Okay, I answer your question.
Okay, thank you, sir.
Oke, terima kasih Caroline. Ada lagi mungkin teman-teman? One last question. Oke, baik. Ada lagi? Baik. Oke. Sepertinya tidak ada lagi ya. Oke,
Ya, ya.
so it is maybe for the theoretical class. We will meet again in 10 o'clock for the practical class. So prepare your MATLAB ya, MATLAB online. Jadi supaya sebentar tidak lagi dibuka dengan lama lagi. Jadi sekarang teman-teman bisa mempersiapkannya dengan baik. Oke, we will meet in 10 o'clock. Oke, silakan rehat dulu sebentar ya untuk 15 menit. Thank you Profesor Imran.
Ya, thank you. So kita jumpa lagi ya.
Ya, kita jumpa di jam 10. Terima kasih.
Terima kasih.
Recording stopped.
Thank you very much, sir.
Thank you.
Yes, sir.